Hello student, I am Dada Pires from Government Degree College, Chingiri. In this session today we are going to learn about the Fermi direct distribution law. What's its main points regarding the FD distribution law and the derivations of the FD distribution law. And this is the topic of the related to Downey University of 5th semester of the sixth paper. So, this FD law come under the statistical mechanics of the 6th paper, physics paper. So, today's learning objective of this is we are learn about the FD distribution law and gain some knowledge about the FD distribution law with an example. So, as we and also gain the knowledge to derive the FD distribution law and how this FD distribution law can be applied to some other particles. So, after these sessions we learn about the FD distribution law, its examples and also on the derivations of the distribution FD distribution law. So, before going we must know some quantum laws and Pauli exclusion principle and Stirling law. As we say in quantum laws which obey the quantum nature, this obey the quantumic law, thus way is called quantum laws. So, Pauli exclusion principle, there is no two electron can accumulate in a single state. So, no electron is only one electron, if it is there another one it should be opposite spin. And Stirling law usually as we see in the previous slides, previous sessions we learn about the Stirling law. So, the log of the factorial of the n is equal to their ni into log ni minus ni. So, this for FD distribution law, so this is applicable to the identical indistinguishable particle. So, they indistinguishable means they obey the same particles. So, and they obey the quantum laws, as the quantum mechanics can be applied here, the Fermi direct distribution, and how the spin is integral of half spin like 1 by 2 h cross 3 by 2 h cross 5 by 2 h cross, like this way integral of the half spin, and they obey the Pauli exclusion principle. So, they only one electron can be accumulated in a state single states, no two electron cannot be accumulated in a single states. So, and they for this FD distribution law example is free electrons in a metal. So, how they conduct the free electrons, and this electron will be the follow the FD distribution law. Let us see how can we derive this FD distribution law, let me see. So, let the Ni be the number of particles in the I state, consider a sheet which consists of n number of particles n1, n2, n3 like this way, and Ni number of particles over the A elementary volume of the cell. So, A is the number of cell is there. So, and each sheet is divided into number of volumes and is filled with the number of particles among A cells. So, Ni accumulate only one particle because they obey the Pauli exclusion principles. So, there is only one particle can accumulate in a single cell. So, remaining A minus Ni cell remains empty. So, this is due to the Pauli exclusion principle. If the one particle applied, so another particle is in another cell, so there is a minus Ni cells will be remains empty, because we know that FD distribution law will obey the Pauli exclusion principle. And this arrangements, the distinguishable arrangement in the ith sheet can be given by this formula, that is A factorial divided by A minus Ni factorial into Ni factorial. So, then in the ith sheet, so what about the total number of arrangements is taken place overall in the system is can be given by just their product of their number can be given is, that is the probability p is equal to pi symbol means it is a product, pi symbol means it is a product, it is a product. So, a factorial, a minus n I factorial and n I factorial. So, as we move further, so on this is substitute in the given we know the Boltzmann entropy relation, that is S is equal to k into log p. So, this is the equation S is equal to k into log p and put the value of log p here. So, S is equal to k into log pi of a I factorial divided by a minus n I factorial into n I factorial. So, this is the Boltzmann distributions law, and the total number of arrangements in a p cells, number of cells can be put in this way. So, we get the and apply this Stirling law here. So, this is the apply for a. The Stirling law says that log n I factorial is equal to n I into log n I minus n I factorial. So, after applying this, make simplify, that is product the numerator log n I plus a I factorial minus n I factorial and minus a I factorial. So, on this taking this value log, put this using for the Stirling law, this one, that is n I log n I minus n I, that is a I log a I minus a I minus a I minus n I into log a I minus n 1. So, after this apply the Stirling law. So, we can be got this simplify a equal to log a I minus a I minus n y. So, log a I minus n 1 and n I log n I. So, after this one, so differentiate with this respect to s, that is ds by k, ds by k equal to sigma dn plus log a I minus n I dn I minus dn I log n I. So, dn I, after taking dn I is common for all. So, then it will be, and also apply for the steady state ds is equal to 0, there is no temperature rises. So, there no internal entropy will not be changed, that is ds is equal to 0. So, after this and simplify log a I minus n I minus log n I is equal to 0. This equation we apply the Lagrange's as we see in the next slide, Lagrange's multipliers and determine multipliers here. So, after this apply log a I minus n I minus lambda minus beta e I, where lambda and beta are the constants, and simplify this lambda and beta and these two terms taken out of this equals means cross the equal sign. So, we get log a I n I minus n I by n I plus lambda plus beta I, taking log outside, that is a and simplify. So, log changes to exponent e to the power of lambda beta I, and this a I minus n I cancel, that is minus 1, that is minus 1 come out of this turns to plus 1 a I. For this equations we can be derived, that is n I is equal to, on simplification of this one, simplify this one, that is n I is equal to a I e to the power of lambda beta e I plus 1. This is the derived equation for the Fermi-Dirac distribution law, that is n I is equal to a I e to the power of lambda to the plus beta e I plus 1. As you see in the previous BE statistics and MB statistics, there is in MB statistics plus 1 is absent, whereas in B statistics the plus sign changes to minus 1. So, but here in FD there is plus 1 will be seen here. So, this all about the FD distribution law. So, let us check some multiple choice questions regarding to this FD statistics. So, in FD statistics the particles are whether they are identical or distinguishable, indistinguishable, both A and B. Which one? Yes, they are identical and indistinguishable. So, in FT statistics, the particle obeys. Which type of spin it they obeys? Whether they have a 0 spin or the integral spin of half or any spin or only even spin. Which they obey? Yes, they obey integral spin of half. So, this FT statistics law does not obey. So, there are some answers are given here. So, 4 questions, that the quantum laws, classical laws, Pauli exclusion principle, integral spin of half. Which one is does not obey? The FT statistic is yes, classical law. It does not obey the classical law. It is obey only quantum laws, Pauli exclusion principle, and as well and also the integral spin of half. Okay, this is all about the FT statistics. Thank you for listening this video.